All right, in this video, we'll actually use the definition of a vector space to prove other properties that are true for a vector space. So prove a few properties using the 10 axioms of vector space. Using the 10 axioms of vector space, we can prove other useful properties that we will use repeatedly in the future sections. All right, so those are not things that you have to prove when proving something is a vector space. Proving the 10 axioms is enough. These will follow. All right, theorem 1.1.1, let V be a vector space. I'm going to take one element V in V, and I'm going to take a real number K. First thing is if I multiply V by the zero scalar, I don't have a choice, I'm going to get the zero element of V. Second, if I take the zero element and I multiply it by K, I'm going to get the zero element. Now, we said that we needed an additive inverse. Well, it turns out that that one will have to be minus 1 times V. So if you multiply V by minus 1, you get its inverse. And then if K times V is the zero element, then either K is the zero scalar or V is the zero element itself. So this is a lot like what we would have for real numbers. If A times B is 0, then A is 0 or B is 0. It's just that since K and V are in different worlds, they're 0 in different ways. All right, so some of these you'll do on a worksheet, some of these you'll do on an assignment. I'm going to prove 2, and I'm going to prove 2 and 4. All right, so let's start with 2. I want to show that k times 0 is 0. So I don't know what k times 0 is, so I'm just going to call it v. So v is k times 0. And then I'm going to start playing with the axioms we have. In these proofs, you really have to be careful and you really have to tell me exactly what you're using. So if I take v to be k times 0, well, I know that adding 0 to anything will leave it where it was. So 0 plus 0, that will be 0. And so here, from here to here, that would be axiom 4. Now, we know that we can distribute a real number over a sum of elements. So here I'm going to distribute. I'm going to get k0 plus k0. And this is by axiom 7. That's the one that tells me that I can distribute scalar multiplication over an addition. Now, each of these vectors I have left are v itself. So what I'm getting is that v equals v plus v. All right, so we're not done yet. We get that v equals v plus v. So let me write it here. And now I'm going to use the fact that I have an inverse. So I'm going to add the element minus v to both sides. All right, so I know this exists by axiom 5. So if I add minus v, I'll get v plus minus v. On this side, be careful. You're actually forced to write it this way, where v plus v was added first because that's what you started with, and then you add what you want afterwards. All right, so by axiom 5 again, this is the 0 element. Just by the way, it's really helpful to have the axioms next to you. I'm not going to show you a split screen because it would get too small, but please have the list of axioms so you could follow along. And then here, I need to parenthesize this in a different way. So I'll want to write that this is equal to this, and that I can do by axiom 3. All right, so v plus. Now this here is v plus its inverse. That is 0 by axiom 4. Axiom 5, sorry, axiom 5, the axiom with the inverse. And then here, this is where axiom 4 plays a role. If I add 0, I get V. All right, so it seems complicated. Really, what I just did, I just added minus V to both sides. So I canceled one V. On one side, I was left with one V. On the other side, I'm left with 0. And that's something that you would do quickly when you're comfortable with V. So if it's vectors or matrices, you would do it quickly, but we don't know what V is. So we really have to rely on our axioms here. So V is V, which was K times 0 is 0. Yep, exactly. All right, so when you do this on an assignment or on the worksheet, I really want you to tell me, or on an exam, you really want you to tell me which axioms you're using at every step. All right, next statement. Sorry. I want to prove that if K times V is 0, then either K equals 0 or V equals 0. All right, so we start by assuming that K times V is 0. And then let's break it down into two cases. Case number 1, K is 0. All right, well, we're done. In that case, this is true, and so we're done. And so where we'll have to do more work is when we assume that K is not 0. Here we need to prove that V is going to be the 0 vector. So I'm going to start with K times V equals 0, and I want to cancel K. How do you cancel K? Well, if K is not 0, I'm going to be able to multiply by a real number. I'm going to be able to multiply by, right, you guessed it, 1 over K. So on this side, I'll get 1 over K times KV. On the other side, I'll get 1 over K times 0. All right, so I want to cancel the K with the 1 over K, but to do that, I first need to put them together as a product of real number, and that's achieved by using axiom 9. All right, then I'll get 1 times V, that's just real numbers, which is equal to V by axiom 10. All right, so at this point, hopefully you see all these axioms, why we need them, because so many things that we feel should be true need those axioms to be true in order to prove anyways. All right, here I have a real number times the 0. Well, 0 element, that's what we did in 2. Anything times the 0 element is the 0 element. And we just proved that, and so we can use it. That's going to be the 0 element, and so that's the 0 element, that's the 0 element. All right, so case number 1, K equals 0, and case number 2, we prove that V equals 0. And so what we have is if KV equals 0, then either K equals 0 or V is the 0 element of vector V, vector space V, sorry. All right, and we're done. So I'm going to use this symbol here to say that our proof is done. You'll see it in the notes at the end of each proof.